Hello everyone, my name is Taimur Bakshi and today I will be talking about software-defined networking. Just to give you a brief outline of the objectives of this talk, I will briefly go through the SDN architecture. We'll look at the history of some of the complementing technologies which led to the development of SDN. We'll also look at some of the requirements that led to the development of SDN in the past few years. We will then review some of the important northbound and southbound protocols within the SDN domain. I will provide an overview of some of the simulation and development tools that we use within the context of software-defined networking. We will then go through some of the important SDN applications which are available at present, and then we will look at some of the open research challenges within this domain. So moving on to the SDN definition, the software-defined networking provides a fundamental shift in device configuration and real-time traffic management, and it's a relatively new networking paradigm. The framework allows for the separation of the data forwarding from the control logic, where the controller is responsible for automatically and dynamically reconfiguring the network devices. Now, this makes real-time network reprogrammability possible, and as you can see from the figure, while conventional networking associates the control logic and data forwarding in a single device, such as a router or a switch, SDN centralizes the control logic at the control plane, where switches act as bare metal hardware, forwarding traffic as per the policies dictated by the controller. So the scheme is well suited for on-demand resource allocation as well as for virtualization applications which are inherent in network architectures such as the present-day data centers. Let's take a look at the SDN architecture. As mentioned earlier, the framework can be divided into three different layers: the application, control, and the data plane. The data plane comprises of individual forwarding hardware, such as network switches. The control plane may comprise of one or more controllers, and the controller quite often is a Linux machine or a dedicated server running control software which is attached to the network through an embedded or sometimes an external management overlay of network cables. At the top resides the application plane, which may run specific applications for traffic monitoring, routing, switching, dictating their requirements through to the network. These requirements are translated using a northbound API to the controller. On receiving these application and service requirements, the controller translates these into universal non-conflicting policies to be applied to the networking hardware. And afterwards, these policies go through a second level of translation. And the controller uses a southbound API, something like the OpenFlow protocol, to automatically translate these policies into low-level device or switch configuration commands. Now, in addition to configuration, the southbound API also provides network state information and an abstract view of the network to higher layers of the SDN architecture, that is the application and the control plane. The framework, therefore, to a great extent relieves the network operator from configuring switches which may run into hundreds, um, if not tens, in larger networks, and makes real-time network programmability possible. Since SDN offers centralized control, network programmability, and network virtualization, we can also trace the development of SDN in each of these domains separately, beginning from the early days of modern computing and networking systems, as shown in the above figure. While I will not aim to describe each of these technologies in detail, there are certainly a few worth mentioning, which I will go through in the following slides. So if we look at centralized control, this could at least be dated back to the early 1980s where AT&T introduced the Network Control Point, or NCP, which offers a centralized database of telephone circuits and out-of-band signaling mechanism. Some other technologies which were relatively recent, include the forwarding and control element separation or forces. This technology employs a control element to formulate the routing table in traffic forwarding elements. And quite recently, in 2007, we have something like Ethane. Ethane computes flow table entries based on access control policies in individual hardware. If we look at some of the technologies within the domain of network programmability, the first one that we can and look at some of the virtualization technologies. Starting in 1998, an idea was proposed named Tempest, and the idea was a separation of the control framework from switches and switch virtualization, specifically within the context of ATM networks, which had open programming interfaces. And then in 2006, we have something called Virtual Network Infrastructure or VINI, which was meant to offer researchers a virtual networking testbed to deploy and evaluate multiple ideas simultaneously, and it could be implemented on different network topologies using realistic routing software as well as user traffic and network events. And then in 2010, we have something called virtualization of network functionality, which is quite popular these days, VNF. Services such as DNS, access control, firewalls, and content caching can be decoupled from the underlying virtual network to solely run as software applications on high volume dedicated hardware and storage. And this is one of the benefits that VNF brings to present day network environments. In 2011 came the Open Networking Foundation, or ONF. The ONF promotes a user driven and open approach to the promotion and adoption of SDN, and the program was formally launched in 2011 by a number of industry giants including Deutsche Telekom, Facebook, Google, Microsoft, Verizon, Yahoo. The approach emphasizes an open and collaborative development process that is driven from the end user perspective. The ONF was also responsible for introducing and documenting the OpenFlow standard, and OpenFlow being one of the primary southbound or controller to network device configuration protocols that we have available at the moment. So what led to the basic, despite having all of these technologies within the domain of centralized network control, programmability, and virtualization, we need to look at some of the requirements which were being dealt with individually and the requirement for an overall framework which caters to a range of operational needs of modern organizations. So starting off with the first one is automation. We needed an increased level of automation to reduce the overall expenditure and facilitate effective troubleshooting as well as reducing unscheduled downtimes and easing off the policy enforcement in the provisioning of modern networks. The other one is dynamic resource management. So using SDN, we can dynamically change the size of the network. We can update the topology and the assigned network resources, which may further aid in network virtualization. And then we have something like network orchestration, particularly useful in network environments such as data centers. So we can orchestrate or control a complete range of network appliances by the hundreds, such as in data centers or larger campus network environments, using a centralized SDN controller. Then something like multi-tenancy support. With the growing proliferation of cloud-based services, tenants prefer complete control over their addresses, topology, routing, and security, and consequently separating the tenanted infrastructure from the underlying hosted services. Something else is open APIs or application programming interfaces. Users having a full choice of modular plugins offering abstraction, defining tasks by API, and not being specifically concerned about the implementation details. So for example, if you are a programmer or a network administrator, all you need to specify is that I need communication between two nodes. So you specify the intent, and this is then consequently furnished without the specification of the exact protocol. So the method is actually determined by the underlying software utility like an SDN controller. The intent is communicated by the user or the operator or network administrator, and this intent is translated into a method and implementation by something like an SDN controller. So that's one of the benefits. A couple of additional things: integrated security, and this is quite a big one. SDN provides us the ability to integrate security devices within the network fabric, leading to greater accuracy in detecting security incidents as well as simplifying management. And then we have integrated resource management, so not just security. In addition to security devices, we can also integrate multiple services seamlessly, such as load balancers, resource monitors, which can be provisioned on demand and placed in the network fabric as and when required. And this overall leads to an improved performance, improved network performance. A control framework which is able to offer the ability to incorporate innovative traffic engineering solutions, capacity calculations, load balancing, and overall offer a higher level of utilization, which can also reduce the carbon footprint and increase the energy efficiency of the SDN environment. And we have something like network virtualization. SDN provides us the ability to provision network resources without concerning about the location of the individual components, such as where the routers or switches are placed within the network. And then finally, it provides us with more visibility and real-time monitoring of the connected devices. Moving on to the program or the application programming interfaces used within the SDN domain. First of all, we have southbound communication protocol, which facilitates communication between the controller and the individual network devices. So between the control plane and individual switches within the network. And this protocol is responsible for translating the application requirements or the service policies into low-level device configuration commands, which are automatically pushed into the network fabric, into each of these network devices from the centralized controller. In addition to pushing configuration, we can also poll different counters within the switches using the southbound protocols. And this is particularly useful for obtaining traffic statistics from individual devices with regards to the present network conditions. Some of the popular southbound protocols include OpenFlow protocol, which, as I explained earlier, was devised by the Open Networking Foundation. Then we have something like the legacy XMPP. This is also being used by vendors. And then finally, some vendors also provide support for netconf and SNMP based management of individual network switches from the centralized control plane. As we explore the SDN domain, we will also realize that the choice of the southbound protocol or communication between the controller and network devices greatly depends on the manufacturer or vendor support for each of these protocols. However, the support for the OpenFlow protocol, which at the moment is a standardized protocol, is quite universal across multiple switch and multiple controller vendors. If we look at how OpenFlow actually works within the context of SDN, so the first and foremost requirement is a compatible switch, an OpenFlow compatible switch which is able to listen to OpenFlow messages and act accordingly. The OpenFlow switch in turn will comprise of one or more flow tables as shown in the figure, and the processing of traffic through the switches is done by matching incoming flows with policy actions such as prioritization of flows, queuing, packet dropping, etc. When a first packet arrives at the ingress port, as shown in the figure by packet in, It is matched with the top priority installed configuration within each flow table. And then we apply the relevant actions such as export it or egress it through a certain outbound port, drop it, or perhaps pipeline it to an additional flow table for further policy implementation. If there is no match for the first packet of that flow, it is called as a table miss, and the packet is buffered and the header is sent to the network controller, asking the controller what policy may be applied for this particular flow. So the flow installation follows a reactive and proactive approach. Reactive, when a query is generated for a particular rule by the switch sent to the controller for further policy implementation. And proactive, where we anticipate traffic coming into the network fabric and we proactively push full flow rules into each of these network devices, with the latter having lower latency as compared to a reactive approach. The northbound API or northbound protocol facilitates communication between the controller and network services or applications. Again, it offers a translation of the application requirements which are to be used by the controller. And the requirements are communicated to the controller in a very abstract way. So it only provides a high level overview of the underlying network. And the programmer is mainly concerned with what to do or what policy to implement without necessarily being concerned about how it's going to be implemented, because conflict resolution is the job of the controller. Some of the popular northbound protocols in this domain in again increasingly depend on the controller manufacturer or vendor. And this is more so in the case of the northbound protocol rather than southbound, because there is no standardization at this level. There is no standardized northbound protocol. Although the ONF or the Open Networking Foundation constituted a working group to standardize the northbound API in June of 2013, at the time of writing there are more than 20 different controllers from multiple manufacturers, each one of them having individual northbound APIs such as RESTful, Java, Python, C, etc., depending on the language that the controller has been developed in. So there is no standardization at this level for the northbound API. Here is a quick example of what the northbound requirements look like. So in this example, we have used RESTful as an example to communicate our network requirements to the controller. We have used something as simple as the curl command, which is basically going to post or push a certain set of rules to enable routing between a laptop assigned with an IP address of 10.0.0.3 with a web server 10.0.0.1. So using these four set of rules, we can actually enable communication between our host and our web server. But as you can see, even using this RESTful protocol, it is not a very intuitive approach, because once again the programmer is worried about how to actually go about and implement each of these individual policies to enable communication between the two network nodes, rather than just specifying the requirement that I need communication between this laptop and this web server, these being the IP addresses, without actually giving the instruction of how to enable it through the network switches. So the approach is not very intuitive, and this is one of the ongoing research problems within the SDN domain as well, which I will discuss later in detail. How can we use the intent rather than the method to specify what we need without specifying how we need? So the northbound API is still very much under development. Moving on to the controller itself, few popular controllers are available. The first one is Rio controller or Ru controller. It's Python based implementation, it's open source, it was developed by NTT in Japan, and it provides a complete network operating system framework, including support for OpenFlow. Another popular platform is the Open Daylight or ODL, which is Java based implementation of a controller. Again, it's open source and it has been developed by industry consortia. So we have multiple companies contributing to ONF and they have come up with this Java based implementation or solution for a SDN controller. It can be used to build programmable and software defined networking applications. And again, it has support for the southbound API or OpenFlow protocol as well as netconf. The simulation and development use of software defined networking again depends on a range of utilities. One of the most important ones is the Open vSwitch. It is one of the most widely deployed software switches and it employs the OpenFlow stack, which runs in the background, which runs on the Open vSwitch instances. And it can be used both as a virtual switch in virtualized network topologies, and it has already been ported to multiple hardware or commodity switch platforms. And additional thing is that it is a part of the Linux kernel since version 3.3.2. With regards to simulation testbeds, among the emulation tools, Mininet is the most prominent. It allows for an entire network to be emulated over single machine or a cluster of machines and distributed nodes and links that utilize the resource of each machine. So it adds scalability to the to emulate larger networks, which may require a lot of computation and bandwidth. The platform simplifies the development and deployment of new services. Say, for example, if we were to model a very basic data center topology, it would require a lot of networking hardware and as well as switching software and controllers to carry out even the most basic experimentation. This is where a cluster-based mininet comes in. Using a cluster-based mininet, which is distributed over several, say for example, machines or laptops, we can actually create multiple instances of pods in each of these laptops. And using the clustering option, we can actually generate traffic and analyze how our topology is going to behave for a particular SDN application to be used in the data center. The simulation testbed using Mininet can be connected to uh, an external controller such as Rio controller or perhaps Open Daylight. In addition to that, it also has built-in support for a OVS or a reference controller. So even in the absence of an external controller, we can actually use an internal controller to carry out with our tests. This is a sample Mininet and Open vSwitch implementation. We can create custom network topology, simply drag and drop different routers and switches into this simulation. And then when we can carry out basic tests regarding connectivity or a specific application that we have developed to be used in the SDN environment. Finally, moving on to the SDN application. So SDN has been implemented in data centers with the aim to reduce network latency and improve control, as well as for intelligent resource provisioning. It has been incorporated in cloud environments specifically to increase service scalability and automated load balancing in multi-tenant shares. It has also been used to increase energy efficiency in data center networking, and it has been used to place selected devices in low power modes to increase the energy efficiency during periods of underutilization. Then we have a broad category of users within the wireless communications domain. So over here we have redesigning of cellular networks such as 5G using SDN to add modularity to the infrastructure. We can also use the information from mobile edge, which can be used to in real time to furnish end-to-end routing policies. And finally, we can offer increased mobility among different mobile carriers, offering permanent connection to the network from the user's perspective. Then we have something like residential networks. SDN enabled one of the first open research problems within the SDN area is the application and service performance. Within this, we have a basic requirement of increasing SDN application awareness and optimizing time critical application services using flow metering. We may use a range of methods for this purpose. We can use OpenFlow protocol, or we can define or derive um, much more sophisticated applications which reside on top of the SDN controller and which can recognize individual application flows to implement per application or per service policy implementation. Then we have the development of SDN monitoring tools, which may aid in evaluating performance gains in heterogeneous or homogeneous network environments. We can also look at embedding network services, like I explained earlier, such as authentication, firewalls, proxies, within the data plane fabric itself, within the switches, so that we can achieve a greater level of optimization in the running of our network. And then finally, we can also look at incorporating information centric approaches or policies which exploit location based data caching, such as the moving of frequently used data by the user um, geographically closer to the user to achieve minimum latency and more optimized operation. Next is controller scalability. This is a very hot topic within the SDN area. We look at ways of reducing the network latency by solving the optimal controller placement problem, which is considered to be a NP hard problem. We have various solutions at the moment which look at minimizing the controller workload with respect to the controller placement. So, how can we minimize the latency between the controller and the switch, as well as how can we basically look at ways of reducing the workload on each of these individual controllers. This may sometimes employ the use of distributed control architectures, which can offer a greater deal of reliability using heuristic or greedy algorithms uh, to basically refactor a larger computer network into smaller networks so that each controller or each divided instance of the control plane is only responsible for managing the smaller subnetwork. And then we have a combination of approaches which can look at optimizing multiple features such as network performance in relation to the placement of the controller and provide a trade off between the performance gains achieved and the operational requirements of the business. Next, we have issues in the switch and controller architecture. Like I explained earlier, the standardization of the northbound API is still undergoing, and there are chances that the northbound API might never be standardized at all. This is because of the benefits that different programming languages and architectures bring to the SDN area. So, studies in this particular avenue include the designing of a vendor-neutral policy abstraction language, which can offer users and operators vertical and horizontal integration with existing network fabrics and with the multiple services running on top of the SDN controller. And then we have issues such as how much of control delegation should be given to the individual switches in the event of a controller failure to increase the resilience and to increase the fault tolerance of a particular SDN framework. And then after that, we have other studies looking at new architectures for controller and switch design, which can look at ways of reducing the memory utilization of individual switches within the SDN framework, and controller architectures which are well responsive to the needs of multiple switches or multiple network nodes with minimum latency. And we have the security or hardening of the SDN framework. So we need to design SDN security reference models. There are none at the moment, which can focus on securing network entities such as the switches or the controller to avoid disruption and security compromises. A single SDN controller or the control plane adds benefit in terms of centralizing network control, but it also creates a single point of network failure and a single point of security concern. If you can take over the controller, then there is no need to take over the network because um, you have basically taken over the whole of the network if you have compromised the controller. Then we have control channel and application controller traffic monitoring and anomaly detection. in specific avenues such as clouds, and the storage of network related information, certain points within the network where we can store this information so that we can easily retrieve it for post event or litigative analysis such as forensic examination. Finally, we have inter or intra-domain SDN interconnection problem. So we have at the present moment used legacy routing protocols such as BGP and OSPF, implemented with a bit of extensions to support inter-domain SDN controller communication. That is basically communication between the controllers residing within the same autonomous system as well as controllers which are belonging to different autonomous systems. How can we securely and efficiently and with minimum latency exchange routing information between two different or disparate SDN domains? And then we have SDN specific approaches which may define new network orchestration applications and information exchange models, something like software defined internet exchange points for the exchange of routing and switching information between multiple SDN domains or multiple autonomous systems. To summarize this present study, this present talk, we have looked at what SDN is and what it is not. So it's certainly not OpenFlow, something that is confused with SDN quite often. The architecture and the requirements leading to the development of SDN, the prominent southbound API or protocols such as OpenFlow, and some of the development and simulation tools using Open vSwitch and Mininet. We also listed some of the existing and expanding applications which have made use of the SDN framework. And then finally, we looked at some of the research problems within the SDN area, which can lead or which can offer undergraduate, senior undergraduate, or maybe postgraduate students something to work on within the computer networking area. Finally, these are some of the references that I have used in the creation of this particular talk. The fifth one is my own personal contribution to the SDN domain, and it's a review article which has been published, which is still actually under publication, but it is available as a provisional document on the Wiley website. So thank you very much for listening, and if you have any questions or concerns, please feel free to ask or email me. Thank you.